7:40 and counting. We're about ready to resume the second part of the afternoon session, the last part of the Centennial Volume Symposium, and to lead that off is Joe Zoeller from Eastman Chemical, who's going to talk about acetochemistry. Yep.
I've titled my talk, Evolving Production of the Acetyls, Acetic Acid, Acetaldehyde, Acetic Anhydride, and Vinyl Acetate, a mirror for the evolution of the chemical industry, but you might say it's a mirror for the revolutions in the chemical industry. Let me just talk a little bit about what we mean when we say the acetyls. We're talking about acetic acid, which is one of the oldest chemicals, by the way, actually used purposely by man. It probably follows ethanol as the second oldest chemical. But actually it's used for recording and recorded use in metallurgy and purifying materials. Actually shows up with the ancient Greeks. So they were using it in an unpurified form. We're also going to talk about acetic anhydride, acetaldehyde, vinyl acetate, because all of these become related together as the product portfolio evolves. It's really one of the largest volume chemicals. To put in perspective, you make about 6 times 10 to the 9 kilos of these acetyls every year as acetic acid equivalent. And these also, like I just said, arose in a co-evolutionary process. And I'm going to talk about that evolution. So we start actually at the beginning. We'll start to think about the period of 1700 to 1910 when people really start to have something written about purified acetic acid. I'm not going to say glacial, we say purified, but about the 1700s. And these are hard days to pick out. It shows up somewhere around the 1740s to 1770s. People didn't have a patent system then, so you couldn't go back and do a search. But they started with the Orleans process where they took waste wine that really didn't smell real good, and did semi-batch oxidations using what is a bacteria that's still very used today if you want to do it that way. It's a acetobacter. But the Germans did what they're probably one of the first cases of applying engineering, and put those bacteria on charcoal and started to do a counter-current oxidation, passing oxygen and air up and the alcohol down, and actually getting very fast rates in a continuous process. So it's probably one of the earliest cases of a nicely engineered process done on purpose. By the late 1800s, it was still coming from nature. They were doing destructive wood distillation to make methanol and make wood alcohol, but got acetic acid and methyl acetate as a byproduct. And that filled a lot of the need as well. And they also got acetone, methyl ethyl ketone, creosote, and charcoal out of that process. There was one problem though. None of these materials could produce glacial acetic acid because people hadn't developed the distillations yet. And what people did at that stage was actually made this glacial acetic acid by taking the purified acetic acid, reacting it with calcium, with lime to make calcium acetate, and then taking sulfuric acid and distilling it away. What a waste. These natural sources actually did though meet our needs for some period of time, but things change. And actually what I'm going to show what happens almost always, you have a triad. As you have a new business start to evolve. That involves both new materials, new technology, new markets. Sometimes it's only one or two, but almost in the case of acetyls, it's almost all three almost happen simultaneously that drive things. I'll kind of put that in and to show how these three factors interrelate. There really were three revolutionary periods in the development of acetyls. The first one happened around 1910 to 1920, and it's acetylene based. And the technology was acetylene hydration and ketene chemistry, and the product was cellulose acetate. We're going to get into that in a second. The second happens around 1950. That's because ethylene becomes available. And also something else happens in the mid-50s that we missed. It's the 40s give us ethylene, but the 50s give us emulsion polymers, things that you're familiar with like Elmer's glue and waterborne paints. This becomes very important, but there's also another chemistry that came along, the Baku chemistry. But now you have two new markets that are very large. This one will eventually outstrip cellulose acetate by about a factor of 2. The third revolution comes in, moving to still the third feedstock, changing to a syngas, using natural gas, or using coal, or even now you think about biomass. And low pressure carbonylation. The market didn't change that much, but there was a new contributor that added about another 12 to 15% requirement. People started using TPA, which is silane oxidation to make bottle polymers. So if we go ahead and move ahead to the settling era, what happened is actually about the mid 1800s, people had finally discovered that you could take lime and coal, heat it up. About the 1870s, this became fairly common, but you could then make calcium acetylide to make acetylene. But no one was thinking about it as a chemical use until about the turn of the century. And the Germans invented a process where you could hydrate acetylene in the presence of mercury. This is a very, if anyone's had the old Marston Boyd, it's one of your first reactions. You'll see the first thing is the mercury and sulfuric acid. And they developed an oxidation for acetaldehyde to acetic acid. That doesn't even require a catalyst, although a catalyst helps. That was commercialized in 1911. To give you an idea about what the demand was at that point, you know, it wasn't $1 million. In 1916, this process was improved by the addition of iron, which made this a much more efficient process. That acetaldehyde oxidation actually would stand around as a key technology for nearly 60 years. Without much change. But the other thing that happened was an engineering improvement. People discovered how to do azeotropic distillation. You could now make glacial acetic acid from any of the old sources as well as this. You can get the water out. And actually, the engineering advance is as important as the chemistry. In the acetylene era as well, there was let's just go make sure I've got that covered. People had discovered that you could make a ketene to make acetic anhydride simply by heating in the presence of phosphates, acetic acid, and this is done in vapor phase. And then you could react it with a returned acetic acid and make acetic anhydride. It's kind of amazing these people were doing this in 1912. And there was another process I'm not going to talk much about, the ethylene diacetate process. People learned by not just adding one acetic acid, but two, and doing the same chemistry you did with water, you can make something called ethylene diacetate, it's 1,1-diacetoxyethane, and crack it to acetic anhydride and acetaldehyde. You can take that acetaldehyde and oxidize it to make your acetic acid you need to keep the feedstock. But the problem was, starting about 1912, 1914, like I said, we didn't have more than 1 million pounds of need. No one, people were inventing things, but they weren't really commercially viable until World War I. Technology can be in place, materials can be in place, but until there's a market, who gives a hoot? When that actually came, the market came from the aviation industry. Actually, let's just say the wartime aviation industry. The plane had been invented, but people used cellulose nitrate on the wing coating for waterproof and also to improve the aerodynamics versus using just linen. And problem with cellulose nitrate is the first time someone hits you with something hot or a flame leaves the engine or a spark leaves the engine, you better find your parachute. They didn't have them then either yet. So you were heading for a fall. But what people had found is that cellulose acetate could be used. And that really was first described in literature about 1865, but it was really an important discovery in about 1904 when someone found how to disperse it by just doing a slight hydrolysis, that you could now disperse it in acetone or acetic acid, and that meant you could apply it as a dope. Think about what people have really done here is they really did the first fiber-reinforced plastic by taking this and dissolving it and placing it on these wingtips. It also produced a sudden large demand for acetic anhydride, because that's how you produce cellulose acetate. Actually, just before the war, some companies were starting to make some tape and things that way, but that was about it. This really caused a boom. What often happens is not only when you have one invention comes along, people then start finding applications for that invention in other ways, in other places. So after World War II, World War I, people were had all of this new capacity, no place to put it, and they started making fibers like rayon. Many of us still have it sitting in our jackets. People started using film like Eastman Kodak. They also started, for the first time, to cast these into thermoplastics. These actually formed some of the first thermoplastics where people were molding items. If you had a plastic in 1920, it was probably cellulose acetate. The other thing that happened is there was some evolution in the way people did things. People recognized early that mercury was, this is not a good thing. people weren't, the riggers weren't doing well. And they found that actually you could move to some other technologies, and you can make acetaldehyde by dehydration. This actually is an old process. People tried to do it for 35 years, and it goes back to the, it's done 1920, but it started actually in 1885. People were trying to work on this, but they couldn't find a good catalyst that would do an endothermic reaction until 1920. In 1940, people found that what the heck, who needs an endothermic reaction? I can do an exothermic reaction, and not only that, it works better. And what that did is this was so good that it shut down all the wood distillation units. They pretty much closed out by the mid-40s, early 40s. The other thing was, so people would use ethanol now instead of wood or the natural resources. The other thing that happened in vinyl acetate first appears in 1921. It was a mercury-based process as well initially, but that didn't last very long. It was replaced by zinc on charcoal, which worked very efficiently at 1 atmosphere at about 170 degrees. And allowed the first full-scale market event, but nobody wanted it. It turned out to be like a 10 million pound plant, and it didn't sell out for 10 years. People didn't have a need. So the production for acetyls as of from the first half of the century, the whole first half of the century, actually could be summarized where we arrived at about 1950. People were using ethanol, wood, which is actually now by 1950 was disappearing. There was still some acetylene plants. In fact, that's one of the things that caused one of the big disasters in Japan, was people doing that chemistry still into the late 40s and early 50s. But people were using acetylene, ethanol, wood to make mostly cellulose acetate as an end product. And that was really where almost all the acetic acid ended up. In 1945, you can actually talk about when does the petrochemical era start. In the U.S. we say 1940, in Europe it's 1950 that the petrochemical era really took underway. So I compromised and called it 1945. But 3 key things happened between 1940 and 1960 that would change the way people make acetyls, really would change the industry as a whole. One is that, of course, the raw material suddenly changed because we now had petroleum. We can make olefins, we can make the BTX stream very easily, benzene, toluene, and xylene. So these all became available as new feedstocks. Technology change. One of the things that is really important to recognize is actually about this period, not around back up to 1938, is the advent of organometallic chemistry and homogeneous catalysis. These actually would have very significant impacts on how people produce these chemicals. And the last thing is a new demand. In the mid-1950s, people developed latex polymers. And those latex polymers are now ubiquitous throughout our world. Everything, tons of things we use. They're used in glues, adhesives, book bindings, paints. So they're one of the most ubiquitous chemicals in the world. And they actually, vinyl acetate, acrylates, and styrene form the backbone of those products. To give you an idea of just what an impact that had, in 1956, the U.S. produced 56 metric tons a year of vinyl acetate. By 1970, it's 356 metric tons, 1,000 metric tons. By 1980, it's 850,000 metric tons produced in the United States. I don't know about anyone, I love that growth. So by the mid-1960s, cellulose acetate was no longer the driving force. The driving force is vinyl acetate. And it also spurred a significant drive to find a way to make acetic acid in larger quantities just to feed this vinyl acetate demand. And what people did is they did turn to 2 new processes that were based upon petrochemical feedstocks. The first one was a butane oxidation developed by the Celanese Corporation and commercialized in 1957. It's a cobalt catalyzed process, homogeneous by the way. 180 degrees, running about 15 to 20 atmospheres. It only does about a 10 to 20% conversion, keeps from over-oxidizing things. Produces a mixture of acetic acid, methyl ethyl ketone, formic acid. In fact, this was one of the big sources of formic acid. Its closure caused the shortage of formic acid for a while. And propionic acid. This was operated actually up until about 2-3 years ago by the Celanese Corporation in Memphis, Texas. BASF also developed a methanol carbonylation in 1960. There was a cobalt methyl iodide process, but here's the real big problem. I don't know about you, I don't want to let it work in those atmospheres, but they commercialized several processes like that at high temperature. It was very expensive to construct those reactors, and they had a fatal flaw. They were only 90% selective based on the methanol, 70 on the CO. Those are not particularly good yields, and the byproduct was that acetaldehyde, which when used in the vinyl acetate process, caused the polymerization process to have problems. So it was not really a very good plant, but it did lead actually to people to start thinking, well, let's just move down the column. We'll talk about that a little later, because that came only 10 years later. It was replaced by a whole other process with another catalyst. Through this period, through about the 1970s, though, acetaldehyde technology as a way to make acetic acid still predominated. Part of what helped us beat the butane process and the methanol carbonylation used at those high pressures and low selectivities was the fact that Zoeller had introduced a new process that involved taking ethylene and oxidatively adding water, which allowed you to make acetaldehyde. It uses a palladium copper chloride catalyst, functions at reasonable temperatures and pressures, about 10 atmospheres. You get a 95% yield of the acetaldehyde out of, from the ethylene. Provided a cheap source of acetaldehyde, so it meant that it never was displaced by those two other technologies as a preferred method, at least not to this point. So that meant that it could stay competitive for this period of time until about 1970. There was some other processes introduced at the same time to try and meet the new vinyl acetate demand. So we've had two new acetic acid processes try and make it on the map, and we've had two new vinyl acetate processes. Celanese had looked back at some of the work with the ethylidene diacetate, that pivotal intermediate from acetylene, and realized they could add acetaldehyde, acetic anhydride, make the ethylidene diacetate. It's an equilibrium process, but they could also crack that to acetic acid and vinyl acetate. It makes a fairly complex reactor system. I probably could have taken some time, and this is something I worked on as part of our chemicals from coal processes, and we found out a way to do a reactive distillation that took the 6 units of operation down to 2 through reactive distillation, and that's something we do talk about in our chemicals from coal. It's not commercial yet, so I didn't include big detail. This actually operated till the late 90s by Celmex down in which is part of Celanese. The exact date I think is 97, but you guys saw the notes that said 96, so I just said the late 90s. But they operated that for a long period of time. This was coincidental with them also shutting down their acetaldehyde facility. The Zoeller process, which is really what in 1960 and 1970 became the predominant process, adopted actually their acetaldehyde process. It used the same chemistry, but just instead of adding water, added acetic acid. That actually stops the thing at the vinyl group, so you don't end up with a second addition. So it yields vinyl acetate. In fact, I'm going to take a second here, because really, if you want to know what is one of the pivotal chemistries to know, because it's really it's important for vinyl acetate, it's important how it goes on to also ask how acetaldehyde was made. This was so pivotal in 1960 that I want to take some time. If you think of what you do here, is you start with a palladium-2. If you have this, it's actually run in the presence of copper and excess chloride. The chlorine actually forms a palladium tetrachloride dianion that should have a 2 minus. You displace one of the chlorides with ethylene. You add you can add alcohols, you can add acid, you can add water to the olefin. It forms it makes a beta oxygenate, which then does a beta elimination to give you a vinyl. You can make a vinyl ether, vinyl ester, or you can make the vinyl alcohol. Vinyl alcohol, of course, immediately tautomized forms the acetaldehyde. I mean, it won't stay as the vinyl alcohol. And there should be, my white arrow isn't showing up here. I moved that over. But the copper, what happens is you've now made a palladium hydride, kicks out HCl, you get palladium 0. Palladium 0 doesn't react directly with oxygen, but it will react with copper too, particularly with a chloride bridge. And what you do is you use copper as your as the oxidant. And then a separate vessel, you just reoxidize your copper. So really, it's a copy. And it's a stoichiometric in copper, but you can regenerate the copper. The modern vinyl acetate process, the one that's still used today, is really a variant of that exact process, where people at Bayer and Herbst learned to, and later National Distillers, have all learned how to take out the copper and use oxygen, put this thing on a heterogeneous support. And what they've really done is they do the same chemistry, except what they've learned to do is by putting in the preferred catalyst, actually palladium gold on aluminum. And what you can use either gold or cadmium to replace copper as the reoxidant, and you can do it on a heterogeneous catalyst instead. And you get actually pretty good yields. This actually, I wrote this as a range. This depends on how old the catalyst is. As the catalyst ages, the yields go down. And that's when you decide, there's a point at which you decide it's time to change this or change in the catalyst, because I can't suffer the yield loss anymore. So people then just change it out. That's what actually determines when to change, is when that yield falls to. It runs about 10 to 15% conversion. And one of the problems there is you have to remove some CO2 co-product. If you leave the CO2 there and don't scrub it, it stops the catalyst. The catalyst eventually dies and forms a carbonate that is not active. So if we approach the period of 1970, when just before the dawn, just at the peak of the petrochemical era, you can start to see what we've really done here is we've now got ethylene is the primary feed. There's a little bit from butane, a little bit from methanol from the BASF, people trying to make it work. But our outlet now mainly is vinyl acetate. Cellulose acetate actually now, instead of being a major outlet, it's only about 30% of the outlet today. And the vinyl acetate represents usually about 55% of the market every year. So we've changed our driver. Now what really happens, it really changed the product cheaper, was some developments made by Monsanto. And this is really a very significant find because, I just told you about 680 atmospheres, 250 degrees. This is running more like 30 atmospheres. Most of it is actually the solvent that is generating the pressure. Really, it's only about 10 atmospheres of CO is actually the true partial pressure. And it runs at about 190, 195 degrees. You can compare that again to the cobalt. That's just a whole different ballgame. The one thing about it is it required about 10 to 20% water. But the other thing is to point out is that it was first order rhodium, first order methyl iodide, and it's an SN2 process. It's really what it's a binuclear process. So versus the cobalt, which had a very complicated dependence on cobalt because only some of the cobalt species were active. And there were multiplicity of materials. Used native added flash to minimize the catalyst precipitation, and they get yields of 99% or greater. Actually, this represented the end of a 57-year quest to actually make something that was commercially viable for methanol carbonylation. The first reports actually started to show up around 1917. 1913 is the first report of someone trying to do a carbonylation. They were using superacids and couldn't recover but 10, 15%, but they patented it. They were trying. It was a beta. The mechanism for that reaction is actually a fairly simple cycle. The rhodium does an oxidative addition to methyl iodide. Again, it's an SN2 type process. The alkylated rhodium species undergoes CO insertion. Addition of a second CO eliminates the acetyl iodide, generates a rhodium dicarbonyl diiodide. The acetyl iodide reacts with water, something very expected. HI reacts with methanol to regenerate methyl iodide. You actually can observe this species, this one, and this one. This one's only so transitory. Once you add CO, the thing pops all the way to rhodium dicarbonyl diiodide. The Eastman process for acetic anhydride may look like a takeoff in that, and it is in a way, but it had some very special requirements because it was not very straightforward to make that extrapolation. Let me talk about what we do here. It's a carbonylation of methyl acetate. If you remember, really what this is used is meant for a cellulose acetate process where you get acetic acid as a byproduct. So you esterify it and then do a carbonylation. This is done actually by reactive distillation. It's one of the first examples of a large-scale reactive distillation being employed. Now they're all over the industry. People use it readily once someone actually showed you could do it. The problems that were faced was in the absence of water, the catalyst never formed because you had no counterion. No counterion, you can't make another anion. So formed a rather unreactive species. The other problem was the catalyst is gradually oxidized, and we have a water gas shift into an aqueous system, which takes care of things. It just doesn't do it here. And the last thing is the iodine cycle is also inoperative. Turns out acetyl iodide and acetic acid don't react. Actually, it's about 3 kcals positive to make that happen. What they did is actually, what we did is added lithium and hydrogen to substitute. The lithium actually gives you a counterion that actually lets this thing work, so you can make the right species, but actually any cation will do that. What's magical about the lithium, or particular about lithium, is that it activates the methyl acetate efficiently. Actually, if you look at this equilibrium reaction of lithium iodide plus methyl acetate to make the acetate and methyl iodide, it has the highest equilibrium constant of all of the counterions. This is actually, this equilibrium constant is cation independent. It's a Lewis acid catalyzed reaction, but it can be rate limiting. This reaction is very fast, thank goodness. And the hydrogen substitutes for the water gas shift, so you get the catalyst produced. What you now have is a mechanism that looks a lot like the Monsanto system, but instead of having one rate limiting step, has 2 rate limiting steps, potentially rate limiting steps, and with a pre-equilibrium. Of course, I don't have to tell anyone who's had to work with that reaction with a pre-equilibrium that can be in 2 rate limiting steps, consecutive steps. It's going to have a mess of kinetics. So. The one thing it also did, though, is it introduced a new raw material. We started using coal at this stage as a resource instead of petroleum. And actually, coal was chosen simply because of where we're located. You could choose any syngas source, but you could use stranded natural gas, but you can also start thinking about biofuels. You can think about petcoke. It's just that that coal was very conveniently available. The other thing is it did use some new technology. That process, it's actually an early demonstration of process intensification, that reactive distillation that I talked about. That's ours. From the modern era, from 1985 to present, really what's happened is just an optimization of those methanol formulation. And 2 new processes have been introduced. One is the Celanese rhodium lithium, and what that really has as an advantage is it lowers water fuel. Remember way back, I told you needed to use an adiabatic flash, but you have 15 to 20% water. I don't have to tell you what most of your energy use is to distill first is water. And if you can get that down, you have a much more efficient adiabatic flash. So that's what the advantage to the rhodium lithium system is. The BP was challenged by this system. I actually looked at it and I think they were challenged. They were very inventive. They went back and looked at the iridium process, because iridium actually at the time was about comparable, but now it's much cheaper than rhodium. But it had a different rate limiting step, and that was that when you try to do the oxidative addition, that's much faster with iridium, but it won't do the insertion step. And the insertion step is very slow, almost. And what they actually did that was kind of neat is they catalyzed the CO insertion, because you have to do this exchange of a CO for an iodide. And what they did is catalyze that step by adding ruthenium. I think that's kind of cool to go ahead and catalyze your one of your rate limiting step with another catalyst. So in conclusion, what I'd like to talk just a second about the future. I think that acetyls, at least for now, have reached a stable production scenario. We have a stable demand, stable technology, but we do have an arriving new set of feedstocks. I think what you might start to see is a migration to those new feedstocks. I also think there may be a time that if you think about the timing, maybe we're ready for another revolution.
Time for a quick question. No questions?
It was
too
so good.